To access the Gaussians, you need to either use the mobile Xterm if you're using Windows, or you can just use the terminal that embedded in Mac. To start building your molecules, you should click File and click New Molecule Group. The default color of this molecule building board is blue-purple color. To make it more easy to accessible, I suggest you to change the background of this molecule board to white color. So in the future, if you need a publication, you do not have to adjust the color of your figure anymore, and it's really clean. To build a molecule, you should use these four tools to have your structure ready. So the first one is right here, element fragment, which is basically our particular atom that you will choose. And the second one is a ring fragment, basically our aromatic, for example, pyridine, benzo, and these kind of things. And also you have our group fragment, which is the organic substance group or organic group, like ethyl, methyl. And lastly, you have this biological fragment, which you can actually choose particular amino acid and so on and so forth. In the future, if you're really into building molecules, you can actually use this custom fragment, which acquire you to build your own fragment and save into the database. However, I do not know if Gaussians with a green plan allow you to do this, but you can definitely try. So the first step of building a molecule or calculating the vibrational mode is to optimize the structure, make sure that the molecule is actually the lowest energy of conformer. So we're gonna start with water. So you can choose oxygen from element fragment and the binding shape, which when you click the molecule board, the water molecule will appears. From the calculation, choose a Gaussian calculation step. And from the first column, which is job type, we're going to change energy to automation. And then in the method, we're going to change a hardware fork, which is default, to DFT. We're going to change the method from B3 LYP to PBE. From basic side, we're gonna choose a custom. The custom basic side is a TZVP, which this combination of method and basic side to be proven that is the best calculation method to estimate the vibrational mode and their location. For the title, we can just choose any name that we want to choose. And after name, we have a period and type MF underline medium. The reason that I choose a medium because you can actually choose a very short, medium, long, and very long. So some calculation might run a little bit longer than 4 hours default, which is a very short. And if you choose a long or very long, then the green plan will now review your job as prioritized. So medium will be the longest job that will be prioritized by the green plan. Although if you calculate water, this is a simple molecule, it can be done almost spontaneously, so you do not need to choose a medium, but just by default, because some molecule like palmitic acid with a substance group might running quite long. So just to become a habit, I put medium. In link, we want to put 20 gigabyte in memory limit and 16 cores in speed shared processors. The reason that we put 20 gigabyte and 16 cores, that's the maximum speed that we can get for individual person. So that will actually make the calculation as fast as it could be. In pub, we can change the MBO check to full MBO. That's the best way to calculate the charge of particular atom if you're interested to find out what the partial charge of a particular atom and how they affect your vibrational mode and so on and so forth. And finally, the final piece of puzzle that we may need is salvation. So if you choose a default and default salvation, then you're going to be defaultly identify the solvent as water. However, you can see that the drop-down list have so many different solvent that you can choose from. That's especially good when you have a particular um, solvent that in mind and how they affect your vibrational mode. And more importantly, you can actually help you to calculate the something called the solvent capacity or solvent cavity and stuff like that. If you do not choose any solvent, then the system will defaultly determine to calculate the molecule in its gas phase. Now everything is set it up, so we can just submit calculation and press save to save the work into the directory that your want the calculation to be saved. One thing is you can see that there is something like DPS L, and on top of that there's some like Scratch. Do not save any data into Scratch because Scratch by definition is kind of rough draft. Sometimes it will be deleted. So do not save anything that is useful in Scratch. You can miss a lot of data to do that. Under Professor Palmer's directory, you can see that we can see a lot of students, right? So for this, you can go into other students' directory to looking for what they calculated. However, you cannot edit or save into other person's directory. You can only save into your own directory. However, there's a one trick that you can do is, for example, let's say Eric's has a pretty complicated molecule that I cannot successfully calculate. What I can do is I can go to Eric's directory, look at the molecule, and then calculate into my directory. Means that I use the optimized structure from Eric's directory and perform the calculation that I needed and save the result into my directory. Uh, Also, when you're making folders for your data, it's important that every folder needs to be one word or one group of word and number combination. You cannot have, let's say, two words. For example, carbon monoxide is a two word. There's a space in between. Just use a carbon monoxide or the CO as name. Carbon monoxide should be one word, no space in between. The reason is if you put a space in between, sometimes the green Gaussians or the green plane will not recognize your folder's name, and whatever job that you've saved in the folder will be discarded or has error message. You cannot access the files correctly. I had this problem 5 years ago when I was undergrad or 6 years ago when I was undergrad researcher. I do not know if it's still problem today, but I suggest not to try it, just to save your time. Now we have the folder that we needed, and then we put the file name and click save and click yes. And now the job is running. When you press open, you can see there's a lot of different file type. So there's a couple of things that actually concern us. First, is a .com file. The .com file basically is outgoing file, which is the job you submitted. So if some molecule has an error or whatever, you can check your .com file. Maybe something was wrong in terms of molecular geometry, charge, and so on and so forth. The log file is the incoming file, which is the calculation that is finished. So that's where you get your results. And that text file is something that I'm going to show you in the future of this video is about the spectra that you're going to download. And the other thing that you might use will be the check file, which are calculating HOMO-LUMO, which will not be covered in this video. So next step is to select the point group with the lowest energy conformer. If you don't know what a point group is, a point group basically is a representation of symmetry of a molecule. In particular symmetry, for the point group, the molecule has the lowest energy conformer, which is important when you optimize any molecule. From that, we're going to use select 2. Under 2, there's a point group. Once you've selected the point group, we're going to enable point group symmetry. So once the point group was enabled, you can see that we can select symmetry at the drop box. And with a simple molecule like water, it's already C2B, which is the lowest energy conformer. But for some other complex molecule, you have to click the symmetrative button to enable to change the symmetry. So most complex molecule might have a CS instead of C1, so you just choose CS, and some molecule has no symmetry at all, will be C1. So if you C1, then you don't have to worry about it. But if you can choose lower energy point group, you need to perform the optimization calculation like before to optimize the molecule to the lowest energy conformer. When we finish a calculation, you can see that from a result on tab and click result summary, we can have some basic information regarding the molecule, including energy, spin, and dipole moment, and so on and so forth. So next step will be our frequency calculation. To do a frequency calculation, right now we have to optimize the structure. Again, we're going to go to a calculation step. In job type, instead of optimization, we're going to choose a frequency. And we do have optimized plus frequency. I do not use that often because first, the structure may not be the lowest energy conformer, and also if it's a really large molecule, there could be a mistake. Means that maybe charge is different or bond length geometry are in wrong position, so it might be error position or error message. And with that, you're gonna waste more time than just optimize first. So once you optimize first and there's no error message, most likely the molecule is good to go for frequency calculation. Usually, it doesn't have a compute Raman by default, but I just gonna select yes every time because I do Raman the most, and also it won't take that much time. And then you're gonna change the title name, usually add a frequency at end by using FQ, and then submit a calculation. After the molecule is computed, again, we're gonna go to a result and the vibrations. From right here, you can see we have a list of vibration mode. It actually represents both IR and Raman, and we can click spectra to review the spectra. You are seeing this range that as it is because I set the range for my default. As such, because this is a region of interest for me, you can reset the range accordingly by click the property, and there's a lot of things that you can actually change in terms of color and range, and also the half waves, full waves half mask, which is actually uh, alters the shape of the peak. Once you have the spectra that you're looking for, then you right click again and save data. This will actually save data to you on Gaussians, and later on you can copy paste into Excel to generate data yourself by using Origin or Excel sheets. What important is when you do a data service, I suggest you to have another folder to be created just for the spectras, because spectra is a text file, and to read the text file, you have to select all files. So in a folder, if you're doing a calculation with .conf file, .log file, and some other file, you're gonna have five files for one calculation. So if you have one molecule calculated, it means that you have three structures, which is optimization with a point group, and frequency. With spectra, if you have both IR and Raman, you're gonna have two of those files, so you're gonna have 17 files total. So if you have, I don't know, a couple of molecules in one folder, it will be hard for you to looking for the text file when you want to copy and paste the spectra. So with that said, I suggest you to open a folder inside the folder of the molecule to just for your spectra, so it will be easier for you to access it. Once you have your spectra created or text file saved, then that's the file that you might looking at, and double click it and click OK on this error message liking button, and then press yes. This will be your text file, and this XY is basically your spectra, and on top there's three lines basically are the table that we saw earlier. So if I have a larger molecule, for example, palmitic acid, then you have a huge table. So these are not the one that you can use to plot, but the spectra XY is. And also there's a derivative of column right there. I don't really use it often. And you have to remember this text file is all in one column. So when you copy paste to Excel sheet, you need to reorganize the data a little bit. So it could be plottable. So first step of building molecules, you need to learn how to replace atom to achieve your geometry. For example, right now I have a benzene ring, And then I'm gonna choose a sulfur, and I will using the binding of sulfur to create binding style. If I want to build a binding selenium, when I click selenium, you can see that in the selenium selection, there's no shape that is actually binding mode, binding shape, which is like a binding selenium, right? A binding file. So what you can do is you can click the selenium atom only and click on sulfur to replace the atom from sulfur to selenium. So now you have benzene selenium. Now we're gonna learn how to modify bond, and I want to build an azide. For azide is N double bond to each other, and there's another single bond to from one side of the N. We don't have azide in this fragment, so I'm gonna use this one to start with, which in my opinion is the closest. So this first step will be replace oxygen and add another N in this molecule. So I choose this structure. First, I replace oxygen with nitrogen and add a nitrogen in the other side of the structure. You can see this structure is actually 3N, but there's one double bond from the other side of nitrogen, which shouldn't be there. So we can delete that bond by clicking delete bond, or just delete, and then clean up the structure a little bit. Now we're gonna click modify bond to modify our bond between the nitrogen. As you can see, there's nothing happen until you actually click on the molecule. So we need to change the single bond of N to double bond. You can search for literature value, what kind of bond length that is, or we have one right here, right? So when I click both nitrogen between the double bond, or at the outside of the double bond, we can see there's actually 1.232 angstrom, which is the bond length. Now we're going to click the other one, the other two nitrogen. So one is the center, one is the other side of the single N bond. There's something that is important when you do any modification, which you have to choose some atoms fixed, some is not. So in my opinion, I always select the important or fundamental atom first. So my first atom always is fixed. So you will now be moving when I modify the bond lines or bond order, which as such, right now, I change the bond order from single bond to double bond, and then change the bond lines from 1.4 to 1.232. When I click OK, see the other nitrogen, actually the bond becomes shorter and it become a double bond, which more represent to azide. Now we're gonna change the bond angle because azide should be a linear, since there's 4 electrons each side of the center nitrogen. We're gonna click on this bond angle and select the bond or the atom that participate. In order, I like to select number 1, number 2, that is should be fixed, and number 3 will be rotated. However, under some circumstance, you want to rotate the center atom, or you want to rotate the first one, and so I, in this case, will rotate the third one because that's the atom by itself, which you need to control. You can change the angle like this, or you can simply just put a number in. Right now it's already 180, but if you put a 180, it will be shaped like this. And that will be your azide. For dihedral angle, in my understanding, is like 3 atom will be a plane, and you change the other atom according to that plane. So to test this, I'm gonna use the bending cell again. We're gonna change the angle of the nitrogen hydrogen at the end, according to the plan that I created by the two carbons and the sulfur. And again, the second and third atom always fixed, and I always fix the important atom that I don't want to stretch. So in this case, I'm gonna only change the hydrogen atom and fix the carbon atom on the aromatic ring. I'll show you later that if you do not fix that, you will be really chaos. And right now you can see the hydrogen bond is rotating according to the plan of the carbon sulfur. Now I'm replacing the hydrogen with CN triple bond, and we're gonna see if we do not set up correctly, how the dihedral angle will actually rotate your molecule. Right now, we're gonna, again, like before, we select the atom inside the group, and we fix the first carbon. And right now, you have to select the rotating group, not rotating atom. But if you select rotating atom only, which is the carbon from the sulfur that are not on the ring, see, you can see that when you rotate it, the nitrogen is fixed, but the whole structure become pointless. And now let's do it again. We're gonna try to rotate the group. See, right now I forgot to fix the first carbon. You can see the first carbon is actually rotating like crazy, and the CN double bond was actually meant to rotate like that. So now we're gonna try again. So we're gonna rotate correctly. So we fix the first carbon. Now the whole group on that substring, which is a CN double bond, is rotating as a whole, which is the way we want it. You can play with this when you're building your molecule and work for your benefit. Through experience, you will learn how you like your bond angle and the dihedral angle or bond length, bond order to be changed. Last thing I want to show you is adding valent. So right now we have for this structure, let's say the literature value asks me to add another chemical bond that is 100 degree from the cover of the benzene ring and sulfur and the bond I can add it. When I click the sulfur from this structure, you can see that we don't have such shape. Of course, you can use, yeah, we don't have the shape. So what you can do is you can add a valent bond on sulfur continuously until you have some structure that is close to what that is. So for example, right here, we have this structure right here, and we're gonna keep adding hydrogen. So what it does is, basically, it gives you the most lowest energy hydrogen that I can add. You can see that right now I have a one hydrogen that is toward to the other direction, and that's the bond angle that I'm looking for from the crazy literature. And what you can do is you delete all other nitrogens and then build up on this hydrogen that left. Of course, you can clean that up a little bit by changing the bond angle to 180 degree. You can actually argue that okay, how about we just add a valent and then change the bond angle to 180 degree. That's totally fine too, right? But sometimes the angle is particularly different from 180. It's just example. And also, if you actually change to 180, you still have to add the valent bond. Otherwise, you have nothing to work with. So that's basically a valent bond that you can add into one molecule. And the benefit of this is when you add more than enough valent, you will have some direction that you're looking for. Lastly, when you add structure, you can choose your adding site basically. You can see that I actually make this molecule larger, which is benzene ring. You can see I click different position of this benzene ring. The highlight position, which is the blue color, or tail color will indicate where you're gonna add onto the structure you're trying to add. For example, if I click on hydrogen and if I add on the bending ring, then I'm adding in hydrogen. Of course, structure doesn't make no sense. Maybe that's inorganic, but that was not work. And then if I add right here, which is the hydrogen, I mean the carbon, then you have a carbon-carbon bond, right? So that's how you actually choose the position. Of course, the bending ring only have so many you can play with, but other one like a amino acid, whatever, it could be really easy to work. So that will be choose your bending set. Lastly, if you want to know how's your job going, you can actually type this command in, which is squue space minus u and your UC ID. When you hit enter, you can see the job status. See, right now I have one job that is running, and it has been run for 2 minutes and 18 seconds. Some other comments, such as cancel the running jobs. I forgot a comment because I have not used that for a long time, but you can Google that in the Gaussian website. And thank you for watching the tutorial, and I hope you have a fun time using Gaussians.